slide, we're gonna be talking about the binary phase diagram. So what comes to mind when you hear the word phase? Maybe it's like a change, a stage, could be anything, right? But in the material context, when we talk about phase, it's a region of space where all physical properties are uniform. Meaning, in this space, in this region, at these conditions, we have the same density, same thermal properties, everything will be the same structure, right? So now that we know what phase is, we're gonna be using a binary phase diagram. And what you can see from the word binary, it means two. So in this case, we're looking at the phases of two elements, two materials combined, an alloy, so we can see how they behave at different conditions. In this case, the binary phase diagram shows us the different phases of an alloy at different compositions and at different temperatures. So you see over here in the diagram, we have in the y-axis we have the temperature, and in the x-axis we have the composition. And we have material A and we have material B. The way you read this graph is, at this point you have 100% of material A, at this point you have 100% of material B. So you move from left to right, you're increasing the concentration of material B that's added onto material A. And if you go from bottom to top, you can see we're increasing the temperature. So at this temperature, the material is a solid, but if we keep on increasing, the material will become a liquid. It will melt at a certain temperature. So right here at this point, we have the melting temperature for material A, and over here is the melting temperature for material B. So below this temperature, the material is a solid. Above this temperature, this material will be a liquid. So you can see there's different sections in the phase diagram. Every diagram will be different, but all of them are read the same way. You can see you have different Greek letters and an L. So the Greek letters, alpha, beta, or whatever letter they represent, they are just the solid phases of the material. For example, the beta, this section, just corresponds to the solid phase of material B. Alpha corresponds to the solid phase of material A. Well, L corresponds to the liquid section. So everything on this section above this line will be a liquid. Regardless of the composition, everything over here will be melted. It's just a liquid. So you can see we have different sections. So we have the solidus and the liquidus line. So the solidus line are just those lines that separate the solids. For example, these ones. Alright? And the liquidus line is the line that separates the liquid from the solid. For example, this line made of these 2 points. So this is the liquidus line and the solidus line. And on the liquidus line, you can see this point, this lowest point, is what we call the eutectic point. This eutectic point is the lowest temperature or the lowest point at this composition when you can go from a liquid to a solid or vice versa, solid to liquid. If you see right here, for material B, so to go to a liquid phase, we have to go all the way to this temperature. While for material A, to go to a liquid phase, we have to go all the way to this temperature. However, at a certain composition of mixing A and B, you can see alpha plus beta, we get to the eutectic point. So this is the lowest temperature. You can see as we increase the concentration of either A or B, both melting points decrease and they converge to this eutectic point. So when you have this material, this alloy of A and B at any composition, you will have two melting points corresponding to each material. But once you're in the eutectic point, instead of having two different melting points, you will only have one. So that's what we call eutectic point, and this is the eutectic line. So at this temperature is the lowest temperature that you can go from solid to liquid. And as you can see, we have different mixtures. We have solids mixtures, we have liquid to solids mixtures. So when materials, sometimes when we make alloys, some materials they don't really dissolve or they don't dissolve too well into each other. So instead of making a new structure, there will just be two chunks of solid just really placed together. So when that happens, when they're not dissolved into each other, then we just write it as those two Greek letters, like addition of those two Greek letters, so like we see here, alpha plus beta. However, when they do dissolve well into each other, when they create a different structure, that's when we define this section with another Greek letter. For example, if A and B would have dissolved really well into each other, they will create a whole different structure. Instead of alpha plus beta, we could have renamed it gamma, delta, or so on. So if we were to see the phase diagram for steel, for example, you can see it has the alpha section, beta, delta, gamma, and so on. And each one corresponds to a different structure, whether austenite, cementite, ferrite, and so on. For this case, however, these two materials seem to not mix well to each other, so we'll just have two different chunks of material mixed together. So if we were to test this, we will see that we will have our both corresponding melting temperature for the mixture. You can see we also have the mixture of liquid plus solid, where it's like more like a transition phase. Some of the materials are already liquid, but we also have some solid chunks of either material B or material A. And as we go beyond those temperature above the liquidus line, then we just have a liquid mixture where everything is just melted and it's just on that liquid phase. So that's it for the phase diagram. You can see it's really simple to understand. So depending on the composition you are, you can find yourself and you can find the properties, the melting temperature, solidification temperature of the alloy that you have. So you can play with the composition and you can see how they will behave at different temperatures. So it so happens that for the tin and bismuth alloy that you guys are working for this lab, the phase diagram is something more similar to this. So once you test this in the DSC, you will get your solidification peaks and you will report all of those data to the wiki so that we can create a phase diagram, the tin and bismuth alloy, for your memo to report. So now let's go into the DSC part. So the first step we're gonna do for the phase diagram is we're gonna measure a sample of around 10 milligrams of the alloy that the tin bismuth alloy we're using. So far we're gonna use the 75% tin and 25% bismuth. So first thing I do is I'm gonna get one of these little pans over here and I'll carefully put it on the scale. And then I'll zero it out. And once it's zero, we'll look for a little sample over here of the alloy to weight. So that's 20 milligrams, so we have to get half of that. And once we get 10 milligrams, then we'll go over to a DC and test. So we already have our sample, it's around 10 milligrams. So we're gonna put our sample over here into the DC. Really careful. So you can see we have our little pan with our sample and a pan that doesn't have anything. And we'll explain about that in a little bit. So we'll just close the DC. And we go over to the computer so we can set up our parameters. So on the name, this will be 75% tin and 25% bismuth. The weight was 8.2 milligrams. And we look where to store the file. So we'll also rename it here 75 tin, 25 bismuth. And we apply. We go to procedure and we check that our procedure is correct. So you see over here, we first start by turning on the DSC, and then it will start calibrating the temperature at 35 Celsius. Once it reaches that temperature, it will start storing all the data. And once it reaches that temperature, it will start increasing the temperature at 20 degrees Celsius per minute. We're actually going to change this to 10 Celsius per minute, all the way to 300. Once it reaches 300, it will be isothermal, meaning the temperature will be constant for 1 minute, and then we'll go back down at 10 degrees per minute back to 35. And once it goes back to 35, the cycle will finish and the data will be stored. All right, so we just click OK, apply once again, go back to the summary, and so that we can start, we'll press play over here. So now we're going for a part for the DSC. So you guys will be using the DSC machine for this lab. So what DSC stands for is differential scanning calorimetry. So this process, basically what it does, it adds heat into the system. So you can see we have here our sample and a reference pan, doesn't have anything. So the heat will be added onto the system and it will measure the heat flow between the sample and the reference pan. So there will be some heat going out and some heat going in, and all of that will be plotted on a heat flow versus temperature graph. So this DSC graph is pretty simple to read, and it can tell us a lot of information for the thermal properties of the material we're testing. So the DSC runs basically like this. So once you put your sample into the DSC machine, you will start increasing the temperature, usually at a rate of around 10 Celsius per minute, or you can go higher or lower. Usually the ones we tend to use is 10 Celsius per minute. So you will keep increasing the heat and at this rate until at this point we find ourselves with this peak, this reaction. So you see over here, we have that when you have the heat going up, we refer that to as an exothermic reaction, and we see the heat going down, we call that an endothermic reaction. So we keep increasing the heat, and we find ourselves with this peak, then we can tell that this is an endothermic reaction, meaning that all the heat is going into the sample that we put in, is being absorbed by the material. So when all the heat is absorbed by the material, it will start breaking down the chains, the bonds, so that it can start going liquid. So this is a melting. So every time you see this, we just know this is a melting peak. So you see it starts at this temperature and it goes over a range of temperatures because we have some chunks that are slightly bigger than others or some are smaller. So all of them will melt at this range of temperature. So however, we can find our peak melting temperature over here. So once we have absorbed all the heat and our material is liquid, we continue to apply heat until we stop it at whatever temperature we determine. Once we get to this point, we go into the isothermal phase, meaning we will keep the temperature constant for a certain amount of time. So we'll just start making this shape up. And then once that time has passed, we'll start now cooling, usually at the same rate that we started heating. So we'll cool back at 10 Celsius per minute. You can see we're decreasing the temperature now. And now we find ourselves with this peak again. So now we'll say the heat is going up. It's an exothermic reaction. So now the material is giving away all the heat that it absorbed. So when the material gives away all its energy, all the heat that it absorbed, it's now solidifying. It's becoming a solid once again. So from here it became a liquid. Now as we're cooling, it's becoming a solid. This is solidification. So once again it becomes a solid, it starts again at a range of temperatures, and we can still find our peak solidification temperature. We'll continue to decrease the temperature at the same rate, and once we reach a certain temperature, usually the temperature we started, just keep isothermal, and the process will finish. We usually do this 2 times to get rid of some of the maybe inconsistencies or maybe errors that we get, but for this lab we'll only run it once. So looking at these 2 peaks, we can find out at what temperature our material melted and at what temperature it solidified. As you can see, these 2 peaks, they're kind of shifted. They're not really on top of each other. They're not really aligned. And that has to do with the dynamic effects of cooling and heating at high rates. When they do this test for alloys, to find out their melting and solidification peaks for the phase diagram, for the binary phase diagram, they usually do a rate of around 1 Celsius per day. So that can take up years, months, just to do one of the alloys at a certain composition. In this lab, however, we're doing at 10 Celsius per minute. So since we're playing along with the rates, our shifts will be slightly shifted. If we were to do a much lower rate, we'll find much data, clear graph, and more stuff that tells us more about the material. And the peaks will start to align a little bit more. So you can see the temperature at which it starts melting is closely aligned to the temperature at which it starts going back to a solid. You can see there's 2 temperatures, but if we were to do this really slow, these 2 temperatures would match. We have your tin and bismuth we're gonna be looking at a graph that has two melting peaks and two solidification peaks. As we discussed in the binary phase diagram part, some elements they don't really mix well. So instead of giving us only one solidification and one melting peak, like the previous graph, we're gonna have two corresponding each to the different material. Of course, they're gonna be slightly lower, just like we saw on the graph. Depending on the composition, you will find yourself here or here or here, and those are the solidification peaks and melting of the material itself. But once you get to a certain composition where we only get one of them, at that composition, whether 50-50 or 45-65 thin and bismuth, we should only get one peak, one solidification peak, and one melting peak for this alloy. So for this lab, we'll give you guys a graph. You can look up on the data on the wiki, so you can estimate, once you do the memo, at which composition we're getting to the eutectic point. Which composition of tin and bismuth will give us this temperature. All the other ones will give us the two individual melting peaks for the alloy in question. So now that this is finished, we have our data here, and we're just gonna analyze the peaks, the solidification and melting peaks, to see what are the values that we got. So we go over here at the top, we look for this one peak analyzer signal maximum, and we place it at the edge where the peaks start. There, and we do it as well for the other peak. And as you can see, we have the two solidification peaks. One is at 128.26 and another one is at 172.82 Celsius. So these are the two peaks that you will report in the wiki. That data is already present there, but it's just for you to know that the temperatures that correspond to both solidification peaks. And the next part, you don't have to report it on the wiki, but you also have to add it in your notebook. You're gonna draw this graph in your notebook, and you're gonna draw the peaks and label them. So let's look at the melting temperatures now. You can see here, this one gives us three numbers. So what they mean is that the first number, the 138, is the temperature at which it starts melting. So there's no one specific temperature, it's a range. So it starts at 138, and the peak it's at 142.82 Celsius. And this number over here that you see here, the 9.065 joules per gram, that's just how much energy you require for that specific part to melt, that specific material. And you can also notice how these peaks are kind of shifted. You can see how this peak corresponds to this melting and this solidification corresponds to this melting, and that the temperature at which it starts solidifying almost corresponds to the temperature at which it starts melting. So as we talked first in the background, in the introduction part of the lab, we discussed how the shift in the peaks is due because of the dynamic effects of the heating and cooling rates that we're using. We're using the 10 Celsius per minute, and if we were to use a much slower rate, then our peaks should have matched at the same temperature. So copy this graph in your notebook, make sure you label all the peaks, you have all the numbers, and it will be part of your grade. So for analysis, just report it, describe what you're seeing, how it looks, how it moves, how the heat flows, and that's pretty much it.